In this lecture, I want to introduce the concept of a magnetic potential, but it turns out what we're going to find is that it's not going to be a scalar potential like the electric field, like the electric potential, but it's actually going to be a vector potential. So that's going to add a little bit of a wrinkle to the discussion. But actually, that's also what makes physics really interesting. And so, if you remember back with electric fields, for the statics case, we found that the curl of the electric field was equal to 0. And then, so this statement implied that the electric field I could relate to this scalar function called a potential. And if you take the gradient of that potential times a minus sign, then you can actually calculate the electric field. So we found this very useful because using a scalar potential was a much easier problem to solve than the vector case with the electric field. And so we could solve for the electric potential, and then all we had to do then was take the gradient of it, and then we were in business. So with the magnetic field, if we look at the curl, it's not equal to 0. Ampere's law says the curl of the magnetic field is mu0 times the current density, J. However, we do have the divergence of a magnetic field is equal to 0. And so the only thing we've done with that so far is to kind of give it a physical meaning, saying that there are no such things as magnetic monopoles, and that every magnet has a north and a south pole. But we can actually take this a step further and define a potential function using this. So we have this nice statement that divergence of B is equal to 0, so that must constrain something. So it turns out, since we're talking about the divergence of the magnetic field, we're going to need a vector potential. So we can write now the magnetic field as minus the curl of a vector potential, which we're going to call A. So what does that mean? Well, first is what if we use this with Ampere's law? So Ampere's law says that I should now have minus the curl of my vector potential. And if I now look at my identities, what I get from this is the gradient times the divergence of the magnetic potential minus the vector Laplacian. So we're taking the Laplacian, basically the second order derivatives, but we're taking those on a vector field, on a vector function, and those are going to be equal to mu0 J. Okay. Okay, so okay. So that's pretty much what we get out of it. And if we now kind of do some of the similar exercises that we had with the electric field, we said there was a scalar function we're called the electric potential, but that kind of left an arbitrary choice of what this potential function should be. And so we could have added a scalar constant to it. So we could have said that the electric potential is not V, but it's V plus a scalar function, a scalar constant, sorry, not a function, but a constant. So I could apply an offset to my electric potential, and when I calculate the electric field, what I get is the gradient of the electric potential minus the gradient of my scalar constant, but it is a constant, so therefore that's equal to 0. And in the end, what I get is the same equation for calculating electric field from electric potential. So nature allows us to add in a constant, basically to shift our electric potential if we want, and we'd still get the exact same electric field result from it. Can we do that for the magnetic case? So let's imagine that our magnetic potential is this other vector function A0, and then we're going to add in the gradient of a scalar function. So now lambda is a scalar, and it's also a function, it's not a constant. Because if it was just a constant, then that would be boring, it would disappear right away. Instead, let's come up with a scalar function, then we take the gradient of it, we turn it into a vector. And so now, if I apply the divergence of A, I should get the divergence of A0 plus the divergence of the gradient of my scalar function. And that divergence of the gradient is just the Laplacian of a scalar function, like so. And if, let's say that the divergence of my magnetic potential is 0, and that means that the divergence of my initial magnetic potential, A0, plus the Laplacian of the scalar function, that's going to be equal to 0, which means that the Laplacian of my scalar function is equal to the negative of my initial magnetic potential. So the interesting thing is that this is very similar to the Poisson equation in electric fields. Poisson's equation said we had the Laplacian of a scalar function, and that's equal to minus the charge density divided by epsilon naught. So just comparing these equations would imply that the divergence of my initial magnetic potential is a source. It is a source of magnetic phenomenon. If I now, okay, so if I kind of keep this analogy going, then if my charge density goes to 0, when the distance from it approaches infinity, so basically I want my charge to go to 0 because I don't want any potential at infinity, then I can look at my Coulomb's, my Coulomb's law equation for the electric potential, which is just the charge density divided by the distance, integrated over the volume. And if I do the same thing for my magnetic case, so I want my source of magnetic phenomenon to go to 0 when I'm very, very far away from the source. So that means my scalar function should have a similar shape as the electric potential function. So I can do the integral of my source divided by R integrated over the volume. And so why did we, I seem to have done something kind of arbitrary. This is A0. So I basically made this statement that the divergence of my starting point magnetic potential goes to 0. That seems to be kind of like an assumption that I'm making. But I'm a little bit justified in making that assumption, because then what I end up with is the Laplacian of my vector potential function is now equal to minus mu 0 j. So I can achieve a similar result, that the Laplacian of my potential function is equal to the source, basically, the source of the phenomenon. So in the electric case, it was the electric potential, and then that was equal to rho over epsilon naught. Actually, minus, sorry. So basically, what I'm kind of waving my hands around is the fact that I'm setting up the problem such that I can get the Laplacian of my potential function, whether it's vector or scalar, is equal to the source of the phenomenon. And the way that I'm doing that is by assuming that the divergence of a vector potential is going to go to 0. Anyway, since this is a Poisson equation, that means basically by analogy I can write out the Coulomb's law for my vector potential, which is mu 0 over 4 pi, the source, in this case a current density, divided by the distance r, integrating over the volume. And this is for a volume. If I want to do this for a surface current, then I would have A is equal to mu 0 over 4 pi, the integral of the surface current density, integrating over the area. Or if I just have a line of current, then I can write out the magnetic potential as mu 0 over 4 pi I, just the current, divided by r dl prime. So all of this, so basically this results that I've now come up with for the magnetic potential, I did mostly through analogy. I said we trust the results of the electric case, and so electric and magnetic phenomena are very similar. They have a lot of the same features to them, so maybe their potential should have similar features, where it's now a 1 over r behavior, and it's also dependent on the strength of the source, whether it's a current or a charge.